All right, let's get started. Good afternoon, everyone. Thanks for coming to this talk. I know it's 4 p.m. after a long day, and it takes a lot to show up at 4 p.m. talk, so I appreciate it. And hopefully, once you guys are done with this talk, you can go get your beers and happy hours. So my name's Ray. I'm from the product team. I work on data engineering products for Databricks, and today with me I have Jacob and Toby. They are here, which they're going to share their use case about using change data feeds capabilities on top of declarative pipelines, hot off the press. The product used to be called DLT, Delta Live Tables, and today we announced that we're going to, after a bunch of improvements, it's next generation, we're going to rename it into LakeFlow Declarative Pipelines. There will be more announcement to come tomorrow during the keynote. Fully backwards compatible. No change to the code required. You're going to get a benefit of the new capabilities. So LakeFlow Declarative Pipelines. Here's a quick agenda. I'll give a very brief 2 to 3 minutes overview of declarative pipelines, why we built it, how that becomes the underpinning component of the whole LakeFlow data engineering products for Databricks. Then I'll dive into change data capture. And I'll give an overview of the functionality, but actually I'll sort of unveil the initial inspiration of why we built that feature, some of the complexities and challenges we ran into, and how we sort of solve these problems in this specific feature, what we call applied changes. Then, the most important part, which is I want to have Jacob and Toby to come on stage to talk about Block, how they are using this particular feature in their use cases and workloads. Square and Block. You guys are as bad at naming things as we are. So, first of all, LakeFlow declarative pipelines. Why we built it? What was the original inspiration? So, maybe before I get started, quick show of hands. How many of you guys already use sort of Delta Live Table now declarative pipelines today? Thank you. And how many of you guys already used the applied changes feature with DLT? So a handful, which is great. Okay, thanks. Put your hands down. So for all the data engineering teams, the data engineers who are doing production data pipelines, what you really want to focus on is this transformation logic of how you want to ingest and process your data. But the reality is that there's a lot of other complexities around that core business logic you have to deal with. So oftentimes you have to deal with different product stacks. If you use batch processing, you need a batch stack. If you do streaming, you need a streaming stack. You have different downstream teams, data science, who want to have unstructured data with a data lake. You have your business BI workloads, you want to structure data. There's just a lot of complexities to integrate with and to deal with. Then on top of that, data is moving towards more sort of like a software dev best practice. So you have to think about how do you version control, but not only your pipeline code, but also how do you version control your data sets, and how do you manage your deployment infrastructure. Then of course, there's governance and there's data quality. You want to make sure that the data is ready for consumption downstream. You want to make sure the right person have the right access to the data. You want to make sure your downstream teams has a catalog to discover all of these data. Then even more complex, for all of you data engineers, it's not always a happy case. So, every week, every month, something goes wrong. There's late arrival, some data was wrong. The business has changed the requirement on this particular transformation and definition. You have to go back in time, clean up data, rerun the entire process. All that replan, rewind, and dependency management gets very complicated. So the original vision of declarative pipeline is, why don't we take care of all of these surrounding complexities, which has nothing to do with your core transformation logic, so that you as a data team, you can focus on deliver the value of defining this unique business transformation logic. So sort of initially why we built declarative pipelines. It's an abstraction layer sitting on top of the Spark and structured streaming engine. Unifies batch and streaming in one stack, abstracts away all of these surrounding complexities that you don't need to deal with the product. Just a bit of a recap. We've renamed that into LakeFlow Declarative Pipelines. It's all branded under Databricks LakeFlow, which is a unified data engineering platform sitting alongside Connect for simple ingestion, declarative pipelines for all of the ETL workloads. We also have Jobs, a fully featured all-purpose orchestrator. So these three pieces become the LakeFlow portfolio. And declarative pipelines been in the market for the past 2.5, 3 years. So we have, many customers are using that in production. If you look at this, slide, you can look at, virtually across all different industry segments, companies of different sizes are finding a lot of value from declarative pipelines, running production-grade pipelines without having to worry about all of these surrounding operational complexities. So that's a quick overview. Let's dive into sort of change data capture. Quick overview, what is change data feeds? Why do people want to do change data capture? So a lot of the times, for you guys, you have your upstream systems, the applications, that's where the data is being generated. Then you need to ingest and move that data into the analytical store for analytics, data science, machine learning. So these upstream are typically transactional databases, right? Like, we announced Lake-based this morning, but similarly, you have Postgres, Oracle, SQL Server, MySQL, these sort of transactional databases. You want to have efficient replication of these transactional data into your analytical store for downstream data science, machine learning, and analytical workloads, right? And typically, it's a two-step process. One is there's an extraction process to get the data from the OLTP databases, which is now the focus of this talk. For those of you guys who are interested in this space, we have LakeFlow Connect, which includes the extraction piece from these transactional databases. Then typically, once you've done extraction, you either throw them as Parquet files into cloud storage systems, or for more real-time use cases, you will stream the change feeds directly into a message bus system like Kafka, Kinesis, PubSub, Azure Event Hub. So the focus of this talk is once you've got all of these change feeds extracted, how do you apply these changes efficiently and correctly into the analytical store for downstream systems to use that? So this is a simple example of a change feeds. It's got a unique ID. It'll give you all of these different changes in a particular column. It'll tell you the type of operations. Is that a insert? Is that a delete? Is that an update? Then very important for change feeds, because ordering is super important for change feed. It tells you the order of these changes being happening. It's critical for you to get the correct replication of the data downstream. So there's also a sequence number. For many cases, it's just a timestamp of when that happened in the upstream OLTP database. And in change data feeds capture, there are two very popular sort of representation of how you want to replicate the data. One is called SCD type 1, the other one is called type 2. Type 1 is very straightforward. Essentially, the result of SCD type 1 replication is whatever is in the target table reflects whatever is in the source table. So in this case, Alice was in Seattle at sequence number 1, and then later on, it's being updated into San Francisco at sequence number 3. So the end result just shows the latest status of where Alice is. So that's type 1. Type 2 is a bit more involved. So in certain cases, for a downstream application, not only you want to know the latest status of what's the upstream table, but you want to capture all the changes along the way. So type 2 will be represented in such a way that you can see that from sequence 1 to 3, Alice was in Seattle, but at sequence 3 and onward, Alice changes into San Francisco. So it captures that entire change history for your downstream use cases. Now, this is applied changes. It's an API as part of the declarative LakeFlow pipelines to apply these extracted change feeds, whether from a message bus or whether from a cloud storage system, into the target table. You can do that in SCD type 1 or type 2. So there are a few things you can configure that. Number one is the source. Where's your change feeds, whether it's Parquet files or a message in Kinesis Kafka. You'll give a key. You have to tell us which column is your key. That's what we use to identify the particular rows to be updated downstream in the target table. Sequence by is super important column for you to tell us the order of the changes. Then ignore now, which is a super important feature that's very hard to get right, which is sometimes the change feeds coming in without all the complete values for each one of these columns. So you just tell, maybe in the previous example, you update the location of Alice into San Francisco, but the change feeds might not have the name information. In these cases, instead of sort of updating into null value, you might want to grab the latest valid value from the previous update. So it's a very important and powerful feature that's very hard to get right. And you can also specify delete and truncate events. So we will figure out how to delete the row or drop the entire table in the target. You can do type 1, type 2, and you can select a subset of the columns to be replicated. And in the case of type 2, you can select a subset of the columns to track for the history. So it's a very simple API. This is a SQL example. These are the configurations you can do on it. We also have a Python interface for that. So that's number one. You have the change feeds. You apply the change feeds into downstream target table. Then we have a second API called apply change from snapshot. Because so many times, some upstream databases don't have change feeds, or you're not doing change feeds capturing the way, then people do a hourly or daily dump of a snapshot from the upstream database tables. So this is the second API, very similar, but the difference is that the source is not a change feed. It's a snapshot of the upstream databases. So you just keep applying a sequence of snapshots. This API will figure out between these different snapshots what has been changed, and similarly apply these changes into the downstream target tables. So the configurations are very similar to apply changes. The only difference is that some of these configurations will not be valid in the case of a snapshot. For example, there won't be now, there won't be deletes, because you are giving us all these different snapshots. We are figuring out the changes along the way. So this is the interesting piece, which I think might be of interest to you guys, especially for many of you guys are not using apply changes today. So before there was apply changes, CDC change feeds is inherently a streaming use case. So what people were doing is they're using structured streaming engine and the merging to statement to do change data capture. So I'll give a very simple example. Going back to type 1, we have these 3 change events. I want to apply downstream so that I know that the latest location of Alice and Bob. So to begin with, it's very straightforward. This is a structured streaming job. The way you implement that is that as soon as you receive the change feeds from the streaming source, you're going to write a logic. You're going to look up the particular key downstream in the target table. If you find a match, you're going to update that row. If you don't find a match, you're going to insert that row. So that's fairly straightforward. But actually, there's a lot of problems and edge cases this part of logic sort of doesn't handle. Number one is that for each of the data processing batch and boundaries, you might have more than one row of the same key arriving at the same time. So in this case, there are 2 rows you need to do to update a particular ID for Alice, ID number 1, which is a key. So first of all, you have to figure out, okay, in this case, which one do I apply? So that's kind of straightforward. You just do a group by and max by the timestamp or the sequence number within the batch before you apply the changes to the downstream target. So that adds a little bit more complexity to your code, but still fairly straightforward, not a big deal. So we'll do that. But that adds a few lines of code to your implementation in streaming. Then the second one, which is out of order, I sort of teed it up a little bit. For change feeds, as you go through the intermediate layer of the cloud storage or a message bus, it almost always will happen where things arrive out of the order. So in this particular case, for example, there was an update event for Alice at time 5 and time 3. But the updates at time 5 could arrive before the updates for time 3. So if you just blindly do the merge statement, you'll first update Alice location to Los Angeles and then to San Francisco. So the end state will be San Francisco. But in this particular case, the end state upstream is actually Los Angeles. So you have to handle the out of order. So how do we do that? We actually store a timestamp as we insert these updates into downstream. So every time we try to update, we will compare what we have in the current change feeds to the last timestamp that's being updated in the table, so that we'll figure out and reordering this stuff. So in this case, it'll correctly update Alice to the latest location as opposed to the arriving order. So that adds a bit more complexity. You have to compare the timestamp or the sequence number with the target before you do the changes. So now 22 lines of code. Then there's deletes. So, apart from insert, update, there's delete. So when you receive a delete event, you need to know that how do I update the downstream to delete the row. So this is very straightforward, just one line of code. But here's the real challenge, which is when you combine deletion events with out of order arrival, things becomes quite complicated. So in this particular case, for example, at time 5, there's an update to change Alice's location into Los Angeles. Then at time 6, there's a deletion event to delete that entire row for Alice. But things could arrive out of the order. So you first receive the deletion event. So you're going to delete the row in the target table. So there's no longer ID 1, there's no longer Alice. Then after that, you receive a record saying, I need to update Alice's location into Los Angeles. So, but there's no row to be updated downstream. That row no longer exists. So what do? You have two options. One is, let me just insert that row. But in this case, you can tell that actually if you insert the row, that becomes a zombie data because that row should have been deleted at time 6. So it won't be the correct results. Then option 2 is that that ID no longer exists in the target table. Let me just drop it. In this case, drop it would have been the right implementation and the correct results. But what if actually there's another insert event that's arriving late that at time, timestamp, let's say number 5.5, that hasn't arrived yet, that actually will eventually put Alice's location at Los Angeles. So if I just simply drop the data, I might have data loss. So it's one way or the other, you're going to get the wrong results. So what do we do with that? So the way we've solved this is that instead of doing deletion right away, we actually perform a soft delete in the target table and continue to track that record so that later on, when we have insert or update events showing up late arrival, we will compare with the timestamp on the deletion events to produce the correct results. But then things get a bit more complicated because you have the soft delete. Then on the query side, you want to filter out these soft deleted events. So we actually create a view on top of the underlying table to give you the point in time correct results from the target of applied changes. Then we build a cron job to periodically clean up these data as time goes on. So then things becomes much more complicated with this out of order for deletion events and also update events. Then all of a sudden, you have a lot more code, and you have to create a view on top of it to filter out the data that's soft deleted you're tracking for order, and at the same time, you need a cron job to clean up these data periodically. And in reality, this is the simplest case that I just described, type 1. If you consider ignore now feature, where not only you need to track the order of a particular row, you actually have to track the order of the particular column, because whenever you receive a null value for a particular column, you have to go look up the previous value record. So the ordering system becomes infinitely more complex when we do that. And std type 2, it'll just, it's way too more complicated. There's no way we can cover that in this particular talk. So the way we build apply changes behind the scene, it's more than 2,000 lines of code. Actually, it's a simple API function that I just showed you guys, and more than 10,000 lines of code to check out for all of these edge cases. So essentially, for everything I just described, basically we turned a few thousand lines of code, quite a lot more testing code, into 10 lines of sort of declarative function for you to apply all of these changes. Behind the scenes, we're handling all of these ordering, tombstone, viewing, cleanup jobs under the hood for you. So that's a quick overview. With that, I want to welcome Jacob and Toby to talk about how Square's been using this functionality at their use cases and company. Toby, thank you.
All right. Hello, mic check. Thanks, Ray. Before we get started, just want to do a show of hands. How many people have heard of Square? I'm glad. We're in SF, so that makes a lot of sense. So most of you probably know Square as your neighborhood POS system. We're in coffee shops, we're in bars, we're in restaurants. But what many of you don't know is actually Square provides some of the best banking products for small businesses out there. We provide credit cards, lines of credit, loans, checking, savings accounts, and I'll be giving 2 examples of how we're using those banking products, as well as some of the things that Ray talked about in our day-to-day work. So I'll be providing some business context behind some of the use cases, tell you a little bit more about the team, and then I'm going to pass it to my engineering colleague, Jacob, who's actually going to talk about the juicy technical details behind the scenes. So next slide. So a little bit more about our team. We're the financial data team. Essentially, we have Our primary customers are those that use banking data within Square. So these are our other product managers that we work with. These are data scientists folks, as well as ML engineers who use our data, build underwriting models, build prediction models, and so on. At a very high level, internally, our goals are to create a single source of truth for our banking data so that we can disperse that banking data across Square, across all of Block, so that we have a unified source of truth. On the other side, externally, we make it easier for product teams to better serve our customers. So this is providing some of the best financial products, best offers to our customers there is, and very competitive on the market. Now let's go to 2 examples. The first one I want to talk about is Square Loans. So many of you guys might have heard this. We're previously known as Square Capital, but essentially we take a look at your on-Square processing data and we provide working capital. Working capital is the lifeblood of small businesses out there. The genesis behind this product is really to help our businesses grow, help them make payroll, help them expand, and really help them succeed while they're on the Square platform. So we ran into an issue where essentially to continue to ramp up this product, to continue to make it better and more competitive for our sellers, we needed to gain more insights into their businesses. As you guys may know, many of the sellers, they don't just work on Square. They might have an e-commerce store that they're on Shopify with. They might do B2B processing. They might do something on the side. So just because we see your data on Square doesn't mean that we know your entire business. And on the flip side, as a small business owner, you like to think of your business as a whole, right? It's not just the different commerce platforms that you're processing on, but rather it's the entirety of your business. So that's really the genesis of this problem, and we knew that we had to incorporate external revenue to our underwriting models. So Jacob's going to talk a little bit more about how we're using Plaid to do that, as well as using Databricks. But essentially, it gives us a more holistic view into their entire business, what the seller cares about. In addition to that, some sellers aren't eligible to borrow from Square at all today. Many of them have given us feedback that the loans offer process, the underwriting process, feels a lot like a black box. They're not getting insights into why they are eligible or they're not eligible for a loan. And therefore, we wanted to expand the eligibility of Square loans so that it gives the sellers more control in their process. They can link their external bank data to give us more information and more insights into their businesses. And in turn, we will provide some of the most competitive financial products out there. So that's really the genesis behind Square Loans. This will tie into a lot of the themes behind deduplicating data as well as incorporating external revenue. Something else that I want you guys to keep in mind is this is a loan offer or a underwriting for a loan is really a decision at a single point in time. Once we have made that decision, we can't go back and retract it. So therefore, the more data that we have, the more accurate it is, it'll help us provide the best offer out there. On the second example I wanted to talk a little bit more about is credit card underwriting as well as line management. So this is another financial product that Square offers to our business customers. This is not unlike the credit cards that you and I have in our pockets today. We provide them with an initial sizing, but I think the more important thing is, unlike a loan, a credit card line or a credit line of credit is something that you can retroactively adjust over time. So as we see more of your business volume, as we see your repayment behavior, we can adjust that credit line either smaller or larger over time. And then we'll talk about some of the products that Ray had discussed in the previous slides. But essentially, we know that different borrowers and different sellers have various needs. Therefore, we wanted to adapt our products to the best of our abilities to provide for those needs. In addition to that, some sellers aren't super comfortable taking out loans. So this is usually something that gets a seller comfortable. Everyone pretty much always use credit cards. And then they also have different day-to-day spending needs that varies from a loan to a different credit card. And therefore, it really helps us use this as an on-ramp to some of our other financial products, as well as continue to use this to gain a more holistic view of the seller's business. So with that, just wanted to provide a little bit more business context behind what Jacob will share more in details, but I'll let him take over the rest.
All right, thanks, Toby. Before I get started, I just want to give a reminder that for the next slides, DLT is synonymous with LakeFlow declarative. We just heard about the rebranding along with all of you today at Keynote. So we're referring to that when we say DLT. And getting started here, I wanted to start with a data mesh architecture diagram. So if you're not familiar, a data mesh is really a set of practices for owning, publishing, and consuming data throughout an organization. And on the top left, you can see we have producer microservices publishing data to Kafka topics. From there, the data is persisted into S3, and we then consume the data in DLT pipelines that are organized using a medallion architecture, where you roughly have different layers corresponding to their own tiers of data quality. In practice, this looks like the bronze layer containing raw, unprocessed data, silver, clean, deduplicated data, and the gold layer, aggregated or joined data. So I'm going to be walking you through two real-life use cases. They will both directly correspond to each of the product slides that Toby presented to you all, and they live in the silver and gold layers of this data flow. So the question I'm going to be trying to answer for these next few slides is, how does Databricks DLT pipelines, specifically using the Apply Changes API, help us implement this architecture? And the first use case I'm going to walk you through is called our silver layer bank transactions pipeline. And the problem statement is, given a stream of bronze transaction data with many duplicates, we need to create a DLT pipeline that exposes a deduplicated view of each merchant's bank transaction history. And at the bottom of the slide, you can see that's a snippet of our transaction event schema. It contains a bunch of identifier fields, as well as not pictured, just would be additional fields for attributes on the underlying transaction, such as the amount or a description of the transaction. And I'm going to walk you through some slides just to illustrate what it looks like to deduplicate this data. So we source the data from Plaid, which is an external banking API provider. They offer a product called the Asset Report, from which we are able to pull merchants' bank statements. And we've got our product teams performing this, pulling an upfront 2 years asset pull, and then on a monthly cadence, they're pulling the last 45 days of assets. And as you can see from that diagram, this necessarily creates a lot of overlapping regions. And that's by design. We want to make sure we don't miss any data. But as a result, we have to account for it and make sure we deduplicate it before exposing it to our downstream consumers. And one other characteristic is that the transactions themselves are mutable. It's possible for an individual transaction to change over time as it's referenced in one asset report to a later asset report. And it's mostly because of that characteristic of the transactions being mutable that we decided to deduplicate by retaining the earliest version of each transaction. So just going back and forth one more time to illustrate that, we're basically just clipping the transactions, the front of each subsequent asset report, because we already have collected the transactions from the previous report. And this is just one other example of how you can have transactions overlapping with one another. In this case, a merchant linked their bank accounts, linked the same bank accounts twice through different product flows at Square. And we have multiple 2-year asset pulls that are mostly overlapping with one another. So in this case, we want to do the same thing. We want to just clip the majority of transactions from the beginning of that second 2-year pull. So we're able to implement this in a pretty straightforward manner using apply changes. This is the DAG for our DLT pipeline. The first two views are performing basic filtering and transformations before we call apply changes in the final node. We're using SCD type 1 with transaction ID as our unique key, and we're sequencing by updated timestamp times -1. That's a trick you can use with sequence by that normally if you were to sequence by the updated timestamp on its own, you would update the transactions in place using the apply changes API as the timestamp field increments, but by using the negative timestamp value, we're just ignoring any updates that take place after the initial version of each transaction. So yes, once again, using apply changes makes this straightforward, which is great. I want to highlight this is kind of an atypical problem that we ran into. It's not that common that you're publishing up to 2 years of transaction data into the past and that transaction data can change over time, but we're able to do it just in several views and an apply changes call. And by using that trick where we sequence by the negative timestamp, we're able to prevent data drift and any other similar types of issues during backtesting. And we've got this pipeline running in production. It's processing a little over 20 million records per week. And one final benefit is that backfills are super easy. We can just point all our historical data into the same pipeline. And by virtue of apply changes handling out of order records, we don't have to do anything else. So this takes us to our second example, which is gold layer credit cards. And here the problem statement was, given 2 streams of data, we needed to create a DLT pipeline that exposes an up-to-date view of each credit card. And our first stream of data is credit card created events. These are emitted each time a credit card account is opened. They contain a number of identifier fields as well as attributes on the account at the time of opening. And our second stream of data is credit card update events, which are just emitted anytime an attribute changes on the underlying account. So those are grouped into several types of updates. We have account status, line size, and account terms updates. And I think this is a really great example to share because this is more of a canonical use case. You have some entity whose state you're tracking over time, and you have a stream of events that correspond to any change in state of that entity over time. So this is a great use case for apply changes as well. And to implement this with apply changes, we can do that in 3 steps. The first of which is transforming credit card update events so they match the credit card created event schema. And for this example, we have a line size update event. We're basically just pulling that line size amount out to a top level field and then setting a bunch of values to null in the middle. That's why owner token, product type, and credit offer ID are all null. We're just setting all the other remaining fields on the created events as null. And we're able to do this because we're going to ignore null updates. I'll get into a little more detail on that just to illustrate it in a few slides. And then our second step is just going to be appending the streams together. So we've got a single stream of credit card created and transformed credit card update events that all share the same schema. And once we've done that, we can just call apply changes as well on that appended stream with account ID as our unique key. And we are sequencing by event time milliseconds, which is just when the event occurred. And we are ignoring null updates. So when we do all those together with apply changes, we're able to output the desired table. And I just wanted to walk through a few slides to illustrate what the ignore null updates portion looks like. For this example, we have a single credit card created and update event. The created event sets all the attributes on the account at the time of opening, like APR, line size, et cetera. And that update is just overriding the line size from 10,000 to 15,000. Pretty much all the other fields on that event are set to null. So with ignore null updates, as you'd expect, we just ignore all those null fields and overwrite the line size to 15,000. And this can just extend to any number of events. This second example is just overriding APR from 1,000 to 1,200 basis points. So yeah, once again, using DLT pipeline with apply changes makes this pretty straightforward. And it's really the ignore null updates, which is doing a lot of the heavy lifting here by handling out-of-order records and determining which fields to set. I just wanted to share an example of what an alternative would look like without DLT pipelines and apply changes. So this is a Spark SQL query using merge into. And it's got a fair amount of the same logic as the DLT pipeline we just constructed. It's unpacking the nested update fields and setting those as top-level fields with a series of coalesce statements. And this works for the most part, but as soon as you run into out-of-order messages, you're going to have issues, as Ray mentioned earlier. And if for any reason an upstream producer is publishing messages out of order, or you have to perform a backfill, then you're kind of out of luck with this approach. You're going to need to reprocess the entire data set in the correct order. And one other downside of this approach is that it doesn't scale in the best way with respect to schema evolution. So in the case that you are adding any new account attributes as fields to your credit card created or updated events, you're going to have to update this query as well, which is just going to add a bit of overhead and is the kind of thing where you could easily imagine someone forgetting to update the query every time the schema changes. So to recap, apply changes speeds up our development process and reduces maintenance overhead. We could see that was the case for two very different examples in the silver layer transactions and gold layer credit card pipelines. All of this is in service of us, my team being able to put high quality data sets into the hands of data science, ML, and product team customers. And there are also benefits we didn't touch upon in these examples from Ray's portion of the talk, such as out-of-order deletes or SCD type 2, that you could potentially benefit from depending on your use case. So we definitely encourage you to check out DLT pipelines with apply changes. Yeah, we're going to bring it back to questions.